So we have seen that line to line voltage, right, on the star side leading the line to line voltage delta side by angle 30 degree, right. We will come to the power units slowly and slowly. Now, this thing you have to understand little bit. Look, what we will do, let the star connection, why means star connection, be the high voltage side shown by letter H. Therefore, look, because why, that A, B, C 3 phases are there. So, A, B, B, C, C, A, several times we have to utter those things. Instead of that, we are telling, in the beginning also I said the star side should be always high voltage side. So, the star connection be the high voltage side shown by the letter capital H. We will high voltage will stand for H, we will take H stand for high voltage, right. The delta connection, the low voltage side shown by letter X, right, will that we will consider X, later we will come to that, right. So, star high voltage side we will take H, but low voltage side we will take X, but not L, because L will stand for line, right. So, delta connection, the low voltage side will be shown by X, right. That means your star side, that high voltage side will represent by H, and delta side, low voltage side will represent them by X, right. And the subscript L, capital L will for line, L stand, capital L will stand for line, for only for this purpose, right. And P, capital P for phase quantities, not for power, just for phase quantities, right, not for power, phase voltage, phase current, like this. It is for this transformer only, that P stands for phase quantities, particularly the voltage, right. N1, number of turns on one phase of high voltage winding, right. That means, later we will show, that means this part, number of turns is N1, and delta side, this side is number of turns in each phase is N2, right. Therefore, N1, number of turns on one phase of high voltage winding, we call high voltage. Instead of A, B, B, C, A N, B N, C N, we will call high voltage side, and N2 is number of turns on one phase of low voltage winding. So, it is number of turns, means it is that number of turns in your either in A to N windings or B to N or C to N, and for delta side it is either A B, B C or C A. So, N1 is the number of turns on one phase of high voltage winding, and N2 is equal to number of turns on one phase of low voltage winding, right. So, instead of NH or NX, we are making N1 and N2, right. Now, little bit you have to understand here, right. Now, the transformer turns ratio is equal to A is equal to N1 upon N2, right. So, it is high voltage by low voltage side N1 upon N2, right, is equal to this is high voltage phase voltage by low voltage side phase voltage. This H stands for, look, now H I told you, H stands for high voltage and P stands for phase. That means VHP means, V capital HP means high voltage side phase voltage, and X is the low voltage side, and P phase, VXP means low voltage side phase voltage. So, that means this A is equal to your high voltage side phase voltage, means if you take this one for any phase, it will be VAN, right, and low voltage, and your low voltage side delta side, it is line and phase voltage same, it will be either VAB or VBC or VCA. So, instead of writing this, we are writing high voltage side phase voltage, that means it will be A to N, B to N or C to N, and this is low voltage side phase voltage, it will be VAB, VBC or VCA. That ratio is N1 upon N2, that is VHP upon VXP. I hope you have understood this, right. The relationship between line voltage and phase voltage magnitude is V high voltage side line voltage is equal to √3 times V high voltage side phase voltage. I mean, if this is your high voltage star side, if this is the high voltage, for example, one example, your VAB is equal to, say, right, √3 times you can take VAN, right, because they are balanced, right, or magnitude wise I am taking, or √3 BN or √3 CN. So, in general, instead of telling like this, we are telling V high voltage side line voltage, right, that means VAB, VBC or VC on the star side, right. So, H stands for high, L stands for line. So, V high voltage side line voltage is equal to root 3 times V high voltage side phase voltage. That means, this case if you take star side, I mean VAB is equal to root 3 say VAN or root 3 VBN or root 3 VCN, because this is balance magnitude only and balance, right. Similarly, for the low voltage side, that is X stands for low voltage side line voltage is equal to low voltage side phase voltage, because it is a delta. This is this side is a low voltage side. So, it is a delta connection. So, line voltage and phase voltage both are same, that is why we are making it as VXL, V low voltage side line voltage is equal to V, X stands for low voltage side phase voltage. I think it is now clear to you, right. Therefore, the ratio of the line voltage magnitudes for star delta transformer is VHL upon VXL, VHL upon VXL is equal to root 3 VHP upon VXP is equal to root 3 into A, right, and A is equal to N1 upon N2, that is root 3 into N1 upon N2 is equal to, I am writing N1 divided by N2 upon root 3. Later we will see what is the meaning of this, right. So, VHL upon VXL is equal to basically root 3 into N1 upon N2, right. This is the high voltage side line voltage by the ratio of the high voltage side line voltage to the ratio of the low voltage side line voltage, that is actually root 3 into N1 upon N2, right. Next, here I am telling only, later we will see. Basically, in dealing with your start delta or delta Y banks, right, I mean start delta or delta Y banks, it is convenient to replace the delta connection by an equivalent star connection. Later we will see that when it is start delta transformer or delta transformer, the delta can be represented by an equivalent your what you call star connection, right, and then we will work only with the one phase. Since for balance operation, the star neutral and the neutral of the equivalent star of the delta connection are at the same potential. So, they can be connected together and represented by a neutral conductor. So, when we are converting, because it is a balance system. So, when we are converting delta to an equivalent star, right. So, that your that neutral point of that delta your the star connection which is converted from delta and the neutral point of the star, they are at equipotential. So, they can be your what you call, they can be your they can be connected together such that represented by neutral conductor, such that they can be represented by a single line diagram. Later we will see that, right. Now, so far we have shown the schematic diagram without the windings. Now, this first you consider the star connection. So, schematic representation of star we have already seen. Now, we will come little bit in detail. The star connection is shown in figure 4a and 4b. I am coming to that. Shows that the single phase equivalent of 3 phase star transformer, and figure 4c shows the single line diagram. Now, as it is a star, so this is your ABC, this is neutral N, this is N. Earlier in the diagram, somewhere I showed that the very first one anyway, but here it is correct. So, here it is neutral, here it is neutral, right. So, everywhere polarity is marked plus minus plus minus plus minus. So, this voltage, this is VAN, this is VBN, this is VCN, and current it is IA, this is your IB and this is IC, right. And this is this is star connection only, star, right. And this side is there your other side also, this current is this secondary side, right. So, current is going out. So, IC, this is IA, this is IB, phase C, phase A, phase B, right. And as it is a balance system, so this can be represented by an equivalent single phase only, only phase A is drawn. So, this is plus minus, this is a polarity. Look, even if I do not mention polarity, if arrow is here means it is positive, right, and if nothing is, and no arrow will be here at the bottom, so it is negative. Whenever arrow tip is showing means it is a positive, even if I missed anywhere, but if arrow is there means it is a positive. So, this is the current IA, and that is the your primary side, and this is that I A is that small a, so your subscript is small a, right, and this is this V A N, this is V A N, this is A, this is V A N, right, this is A V A N. So, A capital N and this is V A N small n, this is your V A N, V A N, this small a n, and equivalent one as star side here it is not shown, but here it is not shown, but star side is always grounded. This is the star star and this is the star star transformer equivalent circuit representation, right. This is a single line diagram of a transformer star star, but later when you study the load flow studies we will see much, but here magnetizing component will be neglected for this representation, right. So, the first one is that schematic representation of star star transformer, this is the single phase equivalent and this is the single line diagram of the transformer, right. Now, we will come to star delta. Now, this is star delta, right. Here this side is star side, right. So, we are not talking about much about high voltage or low voltage now, but this side is always high voltage, this side is always low voltage, right. So, for each phase that number of turns N 1, here also N 1 N 1, but one phase swing is N 1 and this delta side N 2 N 2 N 2, here it is showing N 2, right, and it is star side same as before, plus minus plus minus plus minus. So, this is line to neutral voltage V A N for phase V B N, this is V C N, and similarly for delta side it is A B C, right, and this is equivalent star, I will come to that later on, right, and your turns per phase is N 1, here also line and phase same voltage. So, it is N 2, right. Now, we have just discussed now that V high voltage side line voltage by V low voltage side line voltage is equal to root 3 into N 1 upon N 2. Just now we have seen, right, no equation number is given here. That means, V high voltage side line voltage, right, V high voltage side line voltage, see here I have made it is equal to root 3 times say V A N, right, any line voltage, V A N is the phase voltage, A N, V N is the phase voltage. So, high voltage side is star side, this is star side. So, V A N is equal to root 3 V A N and V low voltage side line voltage is equal to root 3 into V A N, right. That means, this V A N actually equivalent star, right. We are assuming this delta can be made an equivalent star, that is why this in reality this star is not there. For mathematical representation, this is an equivalent star and neutral is available, right, and neutral is available. That means, for delta case if this equivalent star is available, then V your X stands for low voltage side. So, low voltage side line voltage, right, that means VAB, VBC or VC any of this, right, anyway is equal to root 3 times into VAN, that is the equivalent star, that is the your line to neutral, that is the phase voltage, right. So, this one you can write, therefore, VHL upon VXL, that means VHL upon VXL is equal to root 3 VAN divided by root 3 VAN means V capital AN divided by root 3 V small a n, this V, that means VAN is the phase voltage of the star side and this VAN, this is that your equivalent delta has been converted to equivalent star, that is the phase voltage of this equivalent star V small a n, V small a n, root 3 will be cancelled is equal to V capital A N upon V A N. This much you have understood. Therefore, this VHL upon VXL, VHL upon VXL is equal to Vn upon Vn, that means this VAN, V capital A N upon VAN is equal to root 3 into N 1 upon N 2, that means it is N 1 divided by, again we are writing N 2 upon root 3, that is VAN as is to Vn is equal to N 1 is to N 2 upon root 3, as if this turn was N 2, I mean meaning is something like this. I am redrawing for you here, right, just see this one, right, this is your, this point is A, this is A, this is your B and this is C, and equivalent star is like this, right, equivalent like this, and this is neutral, right, and that means stance is n2, this is n2 in each phase, but as we have taken V n upon V n n2 by root 3 as if turns of equivalent star, actually I am making it here, this turns of equivalent star actually it has become n2 by root 3, right. So, this I mean as if after converting into star connection, instead of n2 it has become n2 by root 3. That is why this V n upon, instead of writing this n1 is to n2 upon root 3. So, ratio of line to neutral voltage on the star side to the line to equivalent star line to voltage on the delta side is equal to n1 is to n2 upon root 3. Hope this you have understood. No, if you understood this, things are fine. I have tried all these things to tell you, right. I hope you have understood the meaning of H and X, all have been made it, right, and this one will help you actually to understand this, right. Similarly, for delta star also meaning is same, not doing it for you, but meaning is same, as if this equivalent star that each phase the number of turns has become n2 upon root 3, right. Reality it is not there, but from mathematical point of view it is like that, their meaning is like this, right. So, that means figure 5, now this is that delta side, if you replace by star it is like this. That is why here I have written that figure 5 shows the delta side has to be replaced by an equivalent star connection, right. Now, figure 6 shows the single phase equivalent of star delta transformer, and figure 7 shows the single line diagram. Now, as this side is star, this is also we are taking equivalent star for single line diagram, but not delta, right. That is why this side is A n, capital A n, plus minus this is V n I a, this side turns is n 1, but this side is n 2 by root 3 and I a, because this is its equivalent star is taken, right, and this side is V small a n, right, and this is your single phase equivalent star delta transformer diagram, and this is that your single line diagram. Star is always grounded, not shown there, but you have to show here star is always grounded, and this is delta, this is single line diagram of the star delta transformer. I hope you have understood this, right. So, once again, as if it is an equivalent star from the delta, and star is n 2 by root 3, but not n 2, right, it will be n 2 by root 3, right. Next is, now we will come to the power unit system, right. So, after making all these things, now power unit system will be easier, right. So, power system quantities, because you have 4 quantities mainly, current, voltage, impedance and power, these 4 quantities are there, right. So, power system such as current, voltage, impedance or power are often expressed in power unit values, right. For example, suppose if base voltage is 220 kV, right, suppose any line, suppose you have a 220 kV transmission line, that is base voltage. Suppose you are measuring the voltage of the transmission line, say line to line voltage, suppose it is 210 kV, therefore, in per unit it will be 200 by 220 is equal to 0.954 per unit, it will become a dimensionless quantity, right. So, one major advantage of per unit is that it is properly specifying by properly specifying base quantities, the equivalent circuit of transformer can be simplified, right. If you choose the proper base quantities which expressed in per unit values, the equivalent impedance of transformer whether referred to primary or secondary is the same. This we will see later, we will prove it, that equivalent when you convert everything in per unit, that equivalent impedance with referred to primary or secondary, it will remain same. This is a major advantage, right. Another advantage of the per unit system is that the comparison of the characteristic of the various electrical quantities of different types and ratings, right. So, and the ratings is facilitated by expressing your impedances in per unit based on their ratings. I mean transformer, synchronous generator, line, you are choosing base quantities, you can you can transform all these quantities into per unit values. This is a major advantage, right. And when all the quantities are converted in per unit values, that different voltage level will disappear in your circuit diagram, because that suppose at generating station, say maybe your voltage is stepped up from generator terminal voltage, say 10.6 kV, 10.6 kV to 220 kV, then from 220 kV line will go, then 220 kV by say 132 kV, then 132 by 66 kV, then 66 by 33 kV, and so on. Then we will come to the downstream, the distribution system. So, instead of mentioning all this voltage level, if you choose an appropriate base and all the voltage accordingly will be transformed, then that voltage in your circuit diagram, that voltage levels, I mean different voltage level will disappear. This is a major advantage, right. So, it will be just all these things can be represented by simple impedances, right. So, per unit quantity is equal to actual quantity divided by the base value of quantity. This is equation 2, right. So, that means we are making the things dimensionless, and accordingly judiciously we have to do it, such that all electrical laws will be valid after transforming to the per unit system. So, suppose power SPU, S upon SB, remember this thing, right. I will come to that. S is a complex quantity, but SB is a real quantity, we will come to that. Similarly, VPU is equal to V upon VB, right. The SB is the base power, VB is the base voltage. So, V upon VB, right, it will be per unit. Similarly, per unit current IPU is equal to I upon IB, IB is the base current, and ZPU is Z upon ZB, ZB is also base impedance. SB, VB, IB and ZB, these all are real quantities, right. This is equation 3. I have given the nomenclature, right. So, actually where S in general, that is your S is apparent power, that is volt ampere or kilovolt ampere or megavolt ampere, that is VA, KVA or MVA. V is the voltage, it may be in voltage or in kV. I is the current, ampere or kilo ampere, and Z impedance in ohmic values, right, or phasor or complex quantities, because apparent power, voltage, current and impedance are phasor or complex quantities, right. So, particularly voltage and current, they are actually phasor quantities, right, and that is why written either phasor or complex. And your denominators, example SB, VB, IB and ZB are always real numbers, they are real quantities, right. To completely define a per unit system, minimum your 4 base quantities are required, that is voltage, current, your impedance and power, these 4 quantities are required, right. Therefore, 2 independent base values can be arbitrarily selected at one point in a power system. At least you have to choose 2 base values. Generally, we have seen that we choose 2 things, one is base your volt ampere, another is base voltage, these 2 generally we choose, right. So, usually 3 phase base voltage, 3 phase base volt ampere SB or MVA B, that is MVA base, right, and the line to line base voltage VB or kV base are selected. Generally, these MVA base or line to line voltage kV base generally we select first, right, for the base quantity. This we assume actually for any system, right. Therefore, in order for electrical loss to be valid in the per unit system, right, following relations must be used for other base values. For example, the base MVA is a 3 phase base volt ampere. I told you this is your 3 phase volt ampere, and this base voltage is a line to line voltage, and base CMP is a 3 phase base voltage MVA. That means root 3 kV base into current IB base is equal to MVA base, right. That is IB is equal to base current, from here you can calculate MVA base divided by root 3 into kV base. B suffix B everywhere is used for base. This is equation 4, right. And ZB is equal to kV base upon root 3 into IB, because kV base is equal to line voltage, right. That means, this kV base you divide it by root 3. So, it will be phase base voltage divided by IB is this is equation 5, this is the base impedance, right. Now, substituting for IB, that IB from equation 4, this IB from equation 4 you substitute here, this IB you substitute here, you will get, if you substitute, you will get ZB is equal to kV square base upon MVA base. This is equation 6. This unit is ohm, right. Note that phase and line quantities expressed in per unit values are the same and the circuit laws are valid. This is true. Now, power is equal to SPU is equal to VPU into IPU conjugate, right. Why this conjugate comes, I will come to that when we will study the your load flow studies. This is conjugate comes to capture the your power factor angle when voltage and currents are purely sinusoidal, right. We will come to that for load flow studies. So, SPU is equal to VPU into IPU, that SPU is per unit power, that is PPU plus JQPU, right, all per unit. VPU is equal to per unit voltage and IPU star, that is complex conjugate of per unit current, right. So, star means that complex conjugate, and also VPU is equal to ZPU into IPU. This is equation 8. These are the standard electrical equations, right. Now, the power consumed by the load at its rated voltage can also be expressed by per unit impedance, right. The 3 phase complex power, load power can be given as S load, suffix is load, bracket it is 3 phase power is equal to 3 V phase voltage into IL, the star, that conjugate, that load current conjugate 9, right, where S load 3 phase is equal to 3 phase complex load power, right. V phase is equal to phase voltage and IL conjugate, the star, is a complex conjugate of per phase load current IL, right. So, load power also can be made it like this, right. This is equation 9. V phase into IL, this is the phase load phase current, right, per phase current. So, this is for 3, this is 3 phase, that is why 3 is multiplied, understandable, right. Now, the phase load current can be given as IL is equal to V phase upon ZL, ZL is a load impedance. This is equation 10, where ZL is a load impedance per phase, right. Therefore, substituting IL from equation 10 in equation 9, that means here in equation 9 you substitute IL, that means S load 3 phase will be 3 into V phase, then V phase upon ZL star, that is conjugate, right, is equal to V phase, look, V phase upon ZL conjugate means V phase conjugate divided by ZL conjugate. So, V phase into V phase conjugate will be 3 into V phase magnitude square, right, divided by ZL conjugate, right. I hope you know this, no, V phase V into V conjugate is V square, right. So, V phase into V conjugate, V magnitude V phase square divided by ZL conjugate. That means ZL, here I am writing for you that S load 3 phase is equal to 3 V phase square divided by ZL conjugate. That means ZL conjugate is equal to 3 V phase square divided by S load 3 phase. That means ZL is equal to 3, this is voltage magnitude. So, nothing to deal with that square, as it is. If we take conjugate on both side, you take conjugate on both side, it will be S your conjugate load 3 phase, right. So, that means this equation we are writing, here, then we are writing ZL conjugate is 3 phase voltage square divided by S load 3 phase, that means take conjugate on both sides ZL, this is a real quantity. So, nothing to do with that. So, 3 phi phase square, but this is a complex quantity. So, S conjugate load 3 phase right. Therefore, this we are writing ZL is equal to 3 your magnitude V phase square S conjugate load 3 phase, that is your equation number 11, right. So, also load impedance in per unit can be given as ZPU upon ZL upon ZB as usual. This is equation 12. Now, substituting ZL from equation 11, right, and ZB from equation 6 into equation 12. So, from equation your 11, this expression of ZL, this is equation 11, this ZL you substitute here, and from equation 6 this ZB kV square base upon MVA base 6 you substitute in equation 12, right. If you do so, then your this one it will become ZPU is equal to 3 into V phase square magnitude square divided by S conjugate load 3 phase into MVA base upon kV square base. This is equation 13, right. So, now magnitude V line to line voltage L dash L I have made is equal to root 3 times phase voltage, magnitude of phase voltage, right. That means square it on both sides and bring this one to this side. So, 3 into magnitude of V phase square is equal to magnitude V line to line voltage square. This is equation 14, right. This is equation 14, and next using equation 13 and 14, that means this 3 into V phase square is equal to magnitude VLL square, you substitute here, replace this 3 phase V phase square by this VLL square, because this is equal to this one. So, if you do so, it will come ZPU is equal to V line to line voltage square divided by kV square voltage into MVA base by A star load 3 phase, right. So, simplify, it will be coming like this, right. Now, here your what you call, this is actually this one, that VLL square upon KV square into this one can be written as 1 upon S star load 3 phase I upon MVA base. This equation I am rewriting to your right hand side for your understanding, that magnitude of VLL square upon KVB square, it is okay, and this one we are this part we are writing 1 upon S star load 3 phase by MVA base. So, in bracket we are writing line to line voltage magnitude on KVB whole square into, and this is your S load this conjugate 3 phase by MVA base, that means we are writing this S star, that is conjugate load now PU, no question of 3 phase now, because this part is divided by the base, right, that is why it is PU, and this is also V line to line voltage by KV base. So, this is also VPU, this is your writing actually magnitude VPU square upon S square, this conjugate that load per unit power. That is why this ZPU is equal to, we are writing this equation is equal to ZPU is equal to VPU square by S conjugate load PU. This is equation 15, right. So, this part simple calculation is made it here for your understanding, that Z per unit is equal to VPU square upon S conjugate, this is conjugate load and it is per unit load, right, load per unit load, but it is conjugate, right. This is equation 15. So, thank you.